Welcome everyone to the first seminar of the year. And today we have Professor Madeline with us from Kenyon College. Maddie completed her PhD last year from the University of Wisconsin, Milwaukee, where she worked on various aspects of gravitational wave detection using advanced LIGO, such as low latency pipelines, testing generating activities, and so on. After that, she joined as a faculty Kenyon College in last year. And right now she's at the front line of the advanced LIGO project as a co-chair of LIGO's calibration team. And I guess she'll be telling us all about the calibration of the two detectors that we have operational right now.
Thank you. Yeah, thank you. So I'll be talking today about the calibration of the advanced LIGO detectors. I've listed up here all of my collaborators on the calibration team. And this small list of people comprises the entire calibration team, which is small when you think about the entire size of LIGO. But we are tasked with a very important job nonetheless. So just to begin the talk, if you haven't heard yet, advanced LIGO is here. The advanced LIGO detection era has begun. The two LIGO detectors, our Hanford Observatory, or LHO, and our Livingston Observatory, LLO, are both online. We began our first advanced detector observing run in September, and it actually ends tomorrow. I think, tomorrow. So we've got several months of the most sensitive data we've taken to date, and we're in the process of analyzing this data for gravitational wave signals. So just to give a quick history of where we came from and where we are now with sensitivities, here's a plot showing the initial LIGO sensitivities over our first 5 science runs. So starting in the green with the very first initial LIGO science run, down to the pink here, which is the 5th LIGO science run. And then moving on to our current sensitivities, comparatively in blue, we have the 6th initial LIGO science run. So this is where we ended initial LIGO at. The binary neutron star horizon distance, which is the distance to which we could see a canonical binary neutron star system with an SNR of about 8, was around 45-ish megaparsecs at the end of initial LIGO. And then where we are now, when the advanced detectors came online back in June in one of our early, or I guess it was late engineering runs, but very early advanced LIGO era still, we got down to about the red, which brought us down to a BNS horizon distance of about 65 megaparsecs. And then back in October, our most recent public official sensitivity is this green curve. You can see we brought down that low noise decent amount, and now our BNS horizon distance for this curve was sitting around 72 megaparsecs. So we've come a long way in sensitivity. We're in an era right now where we're taking the most sensitive data to date, both in terms of distance to which we can see and time in which we've accumulated such sensitive data. So the question I'm going to talk about today is how on earth did we get to this type of information about the type of strain per root hertz, or the noise that we're seeing in the noise level of our data from what the actual output of the LIGO detectors in, which is not strain. Our photodiodes don't give us strain. So a fun cartoon of LIGO to give a nice fun intro to what calibration is. If this is one of the LIGO interferometers, which this is a very simplified cartoon diagram of one, and a gravitational wave were to propagate into the projector screen here, that would cause changes in the differential arm length of the LIGO detectors, resulting in a change in the interference pattern at our photodetector. So what we get out of the LIGO interferometer is actually just the counts on the photodetector. And the process of calibrating the LIGO interferometer is taking the counts on the photodetector and doing a unit conversion essentially to get out what was the change in the differential arm length in meters that occurred in order to give us that particular count on the photodiode. So just to define some terminology and what we call certain things, the transmission arm of the interferometer is what we call the X arm. The reflection arm is the Y arm. And then when we talk about the differential arm length of a LIGO detector, we talk about Lx minus Ly, which is this quantity that can change in time due to external sources. So delta L sub Ext is external. Due to external sources, it's just Lx minus Ly. And then if you want to get from that to what we define as strain, you just take the delta L external and divide it by the average arm length. And now, so this is the strain incident on the detector from external sources. This strain includes noise sources as well as hopefully gravitational wave signals. But in calibration, all we care about is getting this number, h external of t, or what I'll probably just refer to as h of t. And then we can pass that off to our data analysts in the collaboration, who can then search that h of t for gravitational wave signatures. All right, so the basic outline of this talk is going to be going through the different goals of calibration and what we've done to strive for each of these goals and what we have left to do to achieve the goals. So to the 0th order in calibration, we need to produce calibrated strain data, right? We need to get h of t for all times in which the detector's in what we call an observation ready mode, or a mode when the LIGO interferometers are locked in resonance in a low noise state, and we have determined from data quality measures and lack of commissioning activities that this is a time period in which science statements could be made. For all of those time periods, we need to actually produce the strain data. So I'll talk about the process of getting the strain data. Additionally, we want to do that with minimal error. Calibration errors, which there's errors in both magnitude and phase of the h of t construction, do have an impact on the science outcomes of LIGO. The science outcomes being statements about detections in terms of SNR, statements about, well, detection statements, I guess, in general, which I guess we quote in terms of false alarm rates usually, but what goes into that are things like SNR, the chi-squared statistic, which is used for detection, as well as parameter estimation statements, statements about what type of astrophysical parameters characterize the source, and also upper limit statements that we make. All of those statements will be impacted by calibration errors. If the calibration errors are small enough, they tend to enter these quantities, SNR particularly, to the 2nd order. So if you get small enough calibration errors, then they really don't have a huge impact on the science outcomes. But if they're too big, they certainly are going to hurt us poorly. In addition, the calibration errors do have frequency dependence. So this is something that people have really just kind of started to investigate. There's a lot of work left to be done. But if you account for the full frequency dependence of the calibration errors, that can have impacts on quantities that look specifically at frequency dependence, such as the chi-squared quantity and the parameter estimation activities. So we want to minimize our errors as well as quantify those carefully across the entire frequency region. And then finally, we would like to do this all in low latency. A big goal of the advanced LIGO era is electromagnetic follow-up. So for binary neutron star systems, for example, if we were to get a gravitational wave candidate from a binary neutron star signal, we've partnered with telescopes. We would want to send that candidate to the telescopes in a quick fashion, such that the telescopes would have a hope of capturing the interesting electromagnetic counterparts that we think are associated with binary neutron star systems, such as GRBs. Since we believe that some of the very interesting electromagnetic information does come very quickly after the merger of a system, we want to make sure that we are able to find our candidates in low latency and distribute our candidates in low latency. This is still an effort that we are, we're not quite low latency as we would like to be in a lot of, mostly it's human-related vetting, but the first step of even being able to do this is you need the strain data in low latency before you could even look for a signal in that data, right? So we want to do all of this in low latency, and looping back to goal number 1, another thing calibration errors impact is the sky map that we pass to our electromagnetic partners. So the shape and the size of the calibration errors will increase and change the probability regions of our sky maps, and therefore impact how well our electromagnetic partners can actually follow up a signal. So ideally, we want the minimal error in low latency to do the best possible science. All right, so first I just want to talk about the process of calibration, what goes into it, and how we get the strain data from LIGO. So to the first order of looking at things, if we just had our LIGO interferometer which is actually not just an interferometer, it's a dual recycled, so we have power and signal recycling mirrors. We have 2 Fabry-Perot cavities in each of the Michelson interferometer's arms, so it's a signal recycling, power recycling, Fabry-Perot Michelson interferometer. The full response of such an interferometer can be modeled, but it is a little bit complicated. It turns out you do pretty well if you model the response of your LIGO, of the LIGO interferometers just as a Fabry-Perot cavity. So what we've got here is we've got some differential arm, delta L, differential arm change, delta L external incident on the detectors. The conversion from that delta L to the digitized photodiode readout, which we call D sub error. This is, well, we'll see why it's the error signal in a second. Sorry. Okay. We call this, well, never mind, I'll come back to that. What we need to model for calibration is what exactly this response is. And the response of just the Fabry-Perot cavity is what we call the sensing function. So we do pretty well by just modeling the response of the whole interferometer as the response of the Fabry-Perot cavity, which you can just think of as a single pole low pass filter, where your pole is sitting at what we call the cavity pole, and that's just roughly 1 over the light storage time in the arms. In addition, you need to have a time delay in there that accounts for things like the light travel time, as well as electronic delays and computer-to-computer communications. And then finally, you need a gain factor for the overall gain of the sensing function. All right, so that's just the response of the Fabry-Perot cavity. And while you can do more complicated things than that, this does pretty well in the frequency band we're interested in. Oh, I guess that's not it. Sorry, I forgot. Yes, you also need to model the electronics at the photodiode readout. So there's one other measurable known term in here, which we'll just call CR of F, which is the modeled electronic readouts. Okay, so let me point out 2 things about the sensing function. You'll notice it's not just a function of frequency, it's also a function of time. And by that, I mean that the sensing function changes at every point in time. And that's something we have to track and model in the calibration. So the 2 time-dependent quantities in the sensing function are the optical gain, which varies with just the amount of light that's stored in the arms. So the pitch and yaw degrees of freedom of the mirrors, the end mirrors of the Fabry-Perot cavity, lead to a change in the total amount of light stored in the arms over time. And as that varies, we need to track that with this optical gain parameter and appropriately model the sensing function with the right gain. That's something we did in initial LIGO too. That's not anything new. Something new to advanced LIGO is the fact that the coupled cavity pole is also actually a function of time. That's a new complication that we just found right before the observing run began. So it turns out that right after we acquire resonance, it takes some time for the optics to equilibrate. And we see the coupled cavity pole, especially at the beginning of stretches where we've acquired resonance. We call those lock stretches. The detector arms are locked in resonance. At the beginning of our lock stretches, we find the coupled cavity pole changes fairly dramatically by about 10, 15 hertz or so, and settles down. And then it stays somewhat stable throughout a lock stretch. So that's also a function of time, something that we need to track and eventually compensate for. So here's just a plot of what the sensing function looks like. This is the Hanford sensing function taken based on measurements made at the beginning of the first observing run. So this is just a Bode plot of magnitude and phase response. You can see this just looks like a low-pass filter with some other features from some electronic stuff. And the cavity pole sits around 300 to 400 hertz, which is about 1 over the light storage time. And then you can see this is the delay.
What do you input as a signal to measure the response from?
Oh, I will talk about that. Yeah. Okay, so the sensing function isn't the end of the story because that's not actually all we have in LIGO. In order to keep the detector in resonance, we actually have to have an active feedback system to colloquially push back on the mirrors at low frequencies in order to keep the detector in resonance. Otherwise, our low frequency noise is loud enough to throw us out of lock soon after we acquire it. So what we do is we actually, the differential arm degree of freedom in LIGO is part of a feedback loop that we call the differential arm control loop, or the DARM is LIGO, or lingo you'll hear a lot in LIGO. So the DARM loop involves sensing function we've already talked about, and then the error signal of the loop is filtered through a set of known digital filters, which we then also spit out what that digitized control signal is. But you then have to actuate that control signal from units of counts here back into units of meters to get a physical delta L control with which the end test masses need to be compensated by. And then you subtract that control signal out. You do the opposite of it to the end test masses, therefore pushing back against the external perturbations. And so what you actually have going into your sensing function, if you will, is a high frequency residual delta L. That's the result of your external perturbations minus the control perturbations that you apply. Okay, so the actuation function is another thing you need to actually model. So basically what we've got is we've got two digital readouts, the error and the control signals. And we've got these three components of the DARM loop, the sensing function, which we discussed how to model already, the loop filters, which are just known digital filters, and then the actuation function, which you need to model as well, because you need to appropriately compensate the DARM error signal for the control signal in order to reconstruct just the external sources, which is all we care about, right? We don't want to search for anything with our control signal. So we have to talk for a minute about the LIGO actuation system. If any of you knew, in initial LIGO, we suspended our test masses from simple pendulum systems in order to isolate them from seismic activity. In advanced LIGO, we upped our game a little. We now have a quadruple pendulum system that suspends each of the end test masses at the ends of the Fabry-Perot cavities. Some language for what we call each stage of the pendulum system, because it will keep coming up, and I'll try not to just use the lingo, but remind people what it is. The top stage is the top stage. The second stage is the upper intermediate mass, or UIM stage of the actuation. The third stage is the penultimate stage, we call the PUM, penultimate mass stage. And then finally, the bottom stage is the test mass stage, which we abbreviated just TST stage. So what we've got here is, right now we don't have any actuators active on the top stage. So when we talk about the actuation, we'll be talking about the UIM, the PUM, and the TST stage. On the UIM and the PUM stage, we have electromagnetic coil drivers as our actuators, which is the same actuation system we used in initial LIGO. And then on the TST stage, the bottom stage, new to advanced LIGO is an electrostatic actuation. So our bottom two stages are fused silica masses connected by fused silica fibers, and then our top stages are metal masses connected by steel wire. And that about exhausts my knowledge of the LIGO actuation system. But important thing to note is we've got an electrostatic drive here on the bottom stage, which is going to come up in a minute. So the overall actuation function, the thing that was A in that DARM loop, is just the sum of the actuations on each of these stages. And here's the plot for Hanford again, showing the magnitude and phase response of the actuation over the whole LIGO frequency band. You can see it's just a linear or log relationship in frequency, but with all of these notches showing up here. I was about to pretend I'm a teacher. Do you guys know why we notch certain frequencies? We can interact. Does anyone know why we have to notch certain frequencies in LIGO? Kip, you're like the kid who knows the answer. All right, go ahead.
To not excite mechanical resonances.
Right. So all these steel wires and silica wires in our pendulum have resonant frequencies. And if we actuate at those frequencies, we're going to, you know what happens when you push at a resonant frequency, right? So we have to notch all those out in our actuation, and that's what all of these notches are. LHO went a little nuts with their notching. The Livingston actuation function doesn't notch quite as many. This is both all the primary resonances and all the harmonics of each of the fibers. Okay, so just like the sensing function had some time dependence to it, new to advanced LIGO is time dependence in the actuation function as well. So the bottom stage, as I said, is now an electrostatic actuator. And due to the large bias voltage on the electrostatic actuator, what we found is that charged ions are building up in the vacuum over time, which are then causing an accumulated charge on the end test mass, which then more charge you have with an electrostatic driver, you're going to get a larger actuation function over time. So we're finding that over time, the gain on the actuation function is steadily increasing, as opposed to staying steady like it did in initial LIGO. So we need to, in real time, compute what that gain is and appropriately correct for it in the actuation function. And this is just the TST stage of the actuation function. So the PUM and the UIM stages, remember those are the electromagnetic actuators, coil actuators. We have noticed a small time dependence, but it's something we're still trying to figure out because we see, for example, 1% deviation in the real part and 1% deviation in the imaginary part in the opposite direction, and we're not sure if this is some calculation numerical thing or if this is real yet. So we need to understand what the time dependence on the PUM and the UIM stages are and decide whether or not those will actually compensate the final calibration. But they're much smaller. So the time, I'll show a plot of this a little later on, but the gain variation on the bottom stage over the course of a few months gets as large as 10% from its nominal initial value. These guys, the gain time dependence stays somewhere around 1–2%. So what we do right now is just inflate the calibration errors by a little bit to account for that until we figure out what to do. All right, so quick summary. The full response of the LIGO interferometer involves modeling the entire differential arm control loop. I'll just say again, this is the control loop that controls the differential degree of freedom. There are actually many loops that control the differential degree of freedom. There are several loops that control the differential degree of freedom. I guess not many, maybe 4. And we assume that the DARM loop can be approximated as just a single input, single output system, and that it doesn't couple strongly to the other degrees of freedom. And that's a decent assumption in LIGO. So just using the DARM loop, we're able to determine the external differential arm changes, delta L external, that occur in LIGO by taking our digitized error signal and digitized control signal, filtering it with the inverse sensing function and then the actuation, appropriate stages of the actuation function, and then also compensating for the time-dependent gains that I just discussed. You'll notice that what is not here is the fact that the cavity pole in the sensing function is a function of time. That's a little more complicated than just a simple gain because these gains are just, real number time series that we can multiply our filter data output by and compensate for that way. The cavity pole varying in time means that we need to have a filter that is updated in time and smoothly incorporated into the calibration. And that's just something that while it's known how one could do this in theory, we just didn't have the manpower or time to incorporate it yet for the first observing run. So that doesn't have a huge impact. It inflates things by a few % in our errors, but that's acceptable given the level we're at. So for the purposes of this talk, you'll just see the whole sensing function grouped together as C of F, and that includes just a fixed value for the cavity pole that we measure at some reference time, and we don't update in time. Okay, so this whole process involves coming up with models for the sensing function and the actuation function, each stage of the actuation function. By the way, PU, I should say this, stands for the PUM and the UIM stages combined. So we track the gain of the PUM and the UIM stages together, and therefore we just do a PUM plus a UIM as that version of the actuation, and then we separate out the TST stage, the bottom stage, because that's the gain we actually want to track separately. Yes?
So for the time-dependent actuation function, you mentioned the ions landing in the ears. How many ions is it, and how are you going to talk about how you measure the change in that?
Oh, I wasn't going to go into details about that. We measure it because we can measure, well, I was going to say a few words. I was going to say that we can measure each stage of the actuation independently using our DARM, by exciting our DARM actuators independently and looking at the response in DARM error, the response in our error signal. And from there, you can pick out what the gain has to be. We don't maybe someone else, maybe there is someone who actually tries to measure that charge. I don't know. It's not something I do. But we can fix it. We can fix the charge buildup by flipping the bias voltage every so often, which I'll have a plot that shows when we did that, and you get back to your nominal value. You discharge it. Yeah. Sorry, that's not a better answer. But in terms of how we actually compute these things, I wasn't going to, geez, there's something. I wasn't going to go into too many details about how we compute the time-dependent factors, but I can point you to a paper on that. Well, at least a LIGO document that should be turned into a paper soon on it. Okay, so the sensing and actuation functions, we basically have a week before an observing run starts where we can put the interferometer in different configurations and take measurements to populate our models for sensing and actuation, and that gives us reference models for the sensing and the actuation functions. And that's what we use for the entire observing run, and that's what's indicated here. So that's what we filter our error and control signals with. And then in real time, we use what we call calibration line injections, or basically sinusoidal injections at several frequencies across the LIGO frequency band and also at different places throughout the DARM loop. And we can use ratios of these known excitations to determine what each of these gains have to be. And that's the vagueness level I was going to go into about that because, well, it's a whole paper by itself. But if you're interested in seeing more on that, I'll pull up the reference. Right, so by monitoring both, this is excitations that we do with the DARM actuators, and then this is an excitation with something called our photon calibrator that I'll talk a little bit more about in a moment. All right, so just putting this all together and kind of what the whole calibration process might look like. First, we've got to make measurements. We put the detector in certain configurations. We've got to measure parameters, then use those to populate our models for sensing and actuation functions. Then the next step is we want to digitize those models. We use FIR filters in the end when we actually filter the error and control signals. So we need to take our frequency domain responses, turn those into FIR filters. And then we need something that's able to actually do the operation of filtering the error and control signals using those FIR filters. We need to have something that is also able to do real-time calculations of the gain factors that I was just discussing, and then put it all together in the right way to give us H of t. So we historically break this effort down into two pieces. We have the frequency domain calibration effort, so-called because they work in the frequency domain. I think this is our S5 paper on calibration. I think that's the one that's up there. But also in prep is at least 3 papers discussing in more detail how we're doing frequency domain calibration in advanced LIGO. Those should be coming out in the next month or 2. But the frequency domain calibration team are people who live and breathe the LIGO interferometers. They work at the sites. They're there to take the measurements when we have the time on the instrument. And it's an effort that is very important and for which, since I am not an instrumental scientist, know too much about, but I will share with you what I do know, and then what I will be focusing on is the second part of this. But I can say a few words. So we use a variety of methods to take measurement. Basically, we have models for the actuation and the sensing. You know, the sensing, I said we've got this single pole filter with some time delay, some gain that we measure in real time. And so what we need to do is we need to have a system for which we can inject some known signal and then from the output determine, for example, what that cavity pole is. That would be our parameter in that model. And then for the actuation, we've got a model for what a quadruple pendulum system looks like, and it's got certain parameters, and we need to have a way to put known things into the detector and then from the output figure out what those parameters are. So we use several different methods. For example, to measure the actuation, we use some techniques, free-swinging Michelson technique, and other techniques that would be discussed in the papers coming out and also in our S5 paper. But kind of our gold standard for calibration in advanced LIGO is our photon calibrator. So our photon calibrator is a laser that sits in the vacuum tubes, and it modulates a beam on the end test mass at 2 points, actually, such as not to cause torque. And so it modulates the laser power, therefore resulting in modulation of the photon radiation pressure on the end test mass, which then causes a known delta L to occur on that test mass. So we calibrate this photon calibrator using, well, techniques you could read about in this paper, for one. And then we can know what that delta L should be. We look at what comes out in our error signal, and we use this technique to measure for example, what the cavity pull is. This is the photon calibrator is what we use to get the sensing function. Additionally, you can use a combo of the photon calibrator while also driving with the DARM actuators at frequencies nearby the photon calibrator driving frequencies. And then you can use ratios of the responses at these frequencies that are right next to each other to figure out independent measurements of each stage of the actuation function. Okay. So that's the frequency domain calibration effort. Very important and very interesting. What I'm going to spend a little more time on is the time domain calibration effort. That's the effort that I lead, so that's what I do know more about. So that process involves digitizing the models and actually writing the code that can do the filtering of the error and control signals. So let me first talk for a moment about digitizing the models. I'll just say, because this question comes up a lot, why do we use FIR filters instead of, for example, IIR filters? So FIR filters are useful for a few reasons. First of all, do I have till 4 o'clock? Yeah, okay. First of all, they're useful because we have things like in our online calibration system, you'll have just a little segment of data that drops out. And we want to fill in that gap of data so that our offline searches don't have a gap in HFT data. And if we were using IIR filters, we would need the entire history of a lock stretch in order to appropriately fill that gap. With FIR filters, all we need is the filter length, which is something like 5 to 10 seconds, which just reduces how much time you need to spend filling literally a 4-second gap in the data. You don't need a week of data to fill a 4-second gap. In addition, we do calibration offline. We have always found the need to recalibrate our data with better accuracy, several times usually. And so for those offline recalibration runs, we would like to be able to parallelize the process as much as possible, taking full advantage of the LIGO clusters available to us. And to do so, you don't want to have the entire lock stretch necessary to get the right answer with an IIR filter. So we're going to use FIR filters. So what I'm going to show here is just the results of taking our frequency domain models, computing an FIR filter with them, and then what I'm showing is just a comparison of the frequency response of that FIR filter to the true answer, the frequency domain model that it was based on. And you can see we've got a technique that gives us very good accuracy for the FIR filters in terms of their faithfulness to the original frequency response. So this is the TST stage of the actuation. In magnitude, we've got relative errors between, we'll call true model answer over FIR filter that are below 10 to the minus 4 across the band. And then the phase response is less than a degree in error. And then the PUM plus UIM actuation filter, which we combine together, is also very, very good agreement. And then finally, the inverse sensing, if you noticed in the equation for computing delta L external, it's not the sensing function, it's really 1 over the sensing function that we need. So what I've plotted here is the inverse sensing function. And then you can see we also have excellent agreement in magnitude and phase. So our FIR filters are very good. They don't really add any additional errors to our final calibration errors. Okay. And then finally, what I'll spend the rest of the time touching on is how do we actually do this? What pipelines do we have in place? What procedures do we have in place to filter the error and control signals? So here's just a generic look at what the workflow would have to look like for a calibration pipeline. You've got to get your error and control signals. You've got to get your calibration lines. You're going to need to demodulate things at the calibration line frequencies in order to do the different calculations you need to do to get the gain factors. So you've got to have a code that can do that. In parallel, you can take your error signal, you'll filter that through the inverse sensing. The control signal, as I said, we split up that bottom stage of the actuation and then the PUM and UIM stages separately, just because we want to track that gain on the bottom stage by itself. So we'll multiply each branch by the appropriate time-dependent gains. So this is we do things, well, you could do it in the time domain or frequency domain, it doesn't matter, I guess, but this is a filtering process, and then this is just a multiplies one time series times another time series process. Add it all together, divide by the arm length, and that gives you h of t. And then just wanted to show you guys what some of these time-dependent factors look like. So those are computed in this calibration pipeline in real time. We get these on a sample-by-sample basis. And what I'm showing here is just over the course of a month from September, I keep losing this. Gosh, okay. From September 11th through November 11th, where each of these notches is a day, we've got what the different calibration factors look like. Well, here we're plotting, this is the TST gain. This is the sensing gain. And I haven't plotted the PUM or the UIM gain, but this is then that coupled cavity pull, which is not something we correct for in the actuation, but we do compute it and track it over time. So you can see, for example, this is what I was talking about. You can see over time that charge builds up and the gain of the TST actuation function builds up over time. What we did right here, about halfway through September, maybe towards the end of September, is at Hanford, we just flipped the sign of the bias voltage, discharged the bottom test mass, and then we were back down at our nominal, this is 1, back down at our nominal value for that gain, and then you can see it started to build over time again. But this is to keep things within something like 10% of what our nominal value is. Basically keep that actuation function within 10% of what we measured it to be at the reference time at the beginning of the entire run. And then at Livingston, actually, we never did this sign flip. So it's actually now sitting above 10%. And it's just annoying to look at, although we know how to properly compute it and correct for it. And then you can see kappa C. Towards the beginning of the run, there was some more fluctuation in kappa C. But you can see mostly it oscillates a bit at the beginning of a lock stretch and then some variation throughout a lock stretch. But all of these variations stay typically within the 10% level. Yes? This was, I believe, changes in the power, the laser power, if I'm remembering correctly. At the beginning, this was the remember this was like the end of the engineering run and the beginning of our first observing run. It took us a little while to settle in. It always does. And then the coupled cavity pull, it stays fairly steady, but you can see it does bounce up and down a little bit. The fact that we don't compensate for this in the calibration yet is not a huge deal because it's not changing too drastically. Okay, so that's an overview of how we make calibrated strain data. I just wanted to talk about the process we're using to do this with as minimal error as possible and show some plots of what the calibration errors look like right now. So to do this with as minimal error as possible, right now we have to use our offline system. Our online system, just because we discovered a lot of these features right before the observing run began, we didn't have everything we needed implemented into our online calibration system before the run began. So we weren't able to correct for example, all of the time-dependent gains in our online calibration. So what we've been able to do is go back and recalibrate all of the data with the time-dependent gains included, or at least we will have that product for people. And then that is how we're able to completely minimize the error of the calibration. The other thing we've seen is that with our online system, sometimes you can have things like data dropouts, which then if you have the input if the data drops out of the input to the online calibration for a second or something, that's going to affect the data for the full history of the FIR filters, which is something like 10 seconds. So that inflates the errors unquantifiably for 10 seconds in the online calibration, which we can once again go back and fix with an offline process. So until our online process is perfect, we needed our offline process to get the minimization in calibration errors. So the entire calibration process we do offline, starting from the error and control signals. We've calibrated data for all observation-ready times. And the errors we get are better than 10% in magnitude and 10 degrees in phase, and I'll show some plots of that. But the latency of this has been on the order of weeks. It's taken us a while to get everything under wraps in order to get the data out with that level of errors. Our online calibration, I believe we've put at 20% in magnitude, 20 degrees in phase. Yeah?
So what is this magnitude and what is this phase of? Is it the input strain to the detector?
I'll show you a plot that might answer the question, I think in 2 slides. Can you ask the question again in 2 slides if I haven't answered it? Okay. So I just want to show, this is almost the same diagram you saw before. Our offline calibration pipeline, it's actually the same pipeline that is used for the online calibration, just run in a slightly different configuration. Since the online calibration desires obviously low latency, we use the GST-LAL software package, which was put together by one of your very own CITA members with some help. So this whole offline pipeline is done using GST-LAL. It does the same process we talked about, just with a few additional things like de-whitening some of these signals that are whitened before they're written out from the instrument. We do some tricks like the actuation function is only relevant at low frequencies, and it's also, since it has all those notches, it's a longer filter. So in order to computationally compensate for that, we can downsample the control signals before filtering them through the actuation, because we don't care about them above a kilohertz, for example. And then upsample things back up before we combine it with the error signal. So this looks pretty much the same as what you saw before. The interesting result is what are the uncertainties of this process. So I'll show a few plots. This is for Hanford. We've got, this plot is showing you, all right, so the solid red line is the ratio of the calibration with no time dependence corrections at all in it. So this is just the reference models from the beginning of the run used. This is at some specific GPS time, but just those reference models, and then it's compared to, divided by what the perfect calibration would be. So the calibration that accounts for all the time-dependent gains as well as that cavity pull that varies in time. So you can see there's a systematic error, which is shown by the solid red line, which leads to at most something like 5% deviation from what the perfect calibration should be. And on top of that, there's uncertainty in the calibration. So here's the systematic error, and then the statistical error would be the dotted lines showing you the plus or minus what number from that systematic. So if you want to think about it as the overall error as just one number across all frequencies, we're within 10% in magnitude and 5 degrees in phase. And this is our calibration errors for, if you're part of LIGO, this is the C01 frames. These are the frames that, this is the H of T that has no time dependence corrections in it. Now, if you correct for some of the time dependence, so if you correct for the TST gain, the varying gain in the TST actuation, and the varying gain for the sensing function, you get this level of improvement. So now our systematic is a little better. Yeah, a little better, right? I have to go back and forth. Oh, maybe it's about the same, right? So here's 1. All right, well, overall you get something like maybe better than 8% in magnitude and still about 5 degrees in phase. And then to do even better, you really need to account for all of the time dependence. So that includes the time dependence of the coupled cavity pull, as well as the PUM and UIM stage gain time dependences. So for that perfect calibration, you're just left with the uncertainties, which gets you down to something like 5% in magnitude and just a few degrees in phase. Now the reason really no one in LIGO but the calibration team cares about getting from necessarily this down to this is that once you get below 10% in magnitude and 10 degrees in phase, you really aren't affecting any of our science goals that much. But it's our job to get things as good as possible, so we're going to strive to get to this perfect calibration level, ideally in our online system. And then I just want to show for Livingston what we've got for these same 3 scenarios. So no time dependence at all. Notice we have a much larger systematic error in the low frequency region for Livingston. That's because due to technical and manpower issues, we just didn't get as much time on the instrument to take measurements to accurately calibrate the actuation model. So with more time to get measurements, we could bring down some of those systematic uncertainties. But then once you include, also the other reason is because at Livingston, we did not do any of the sign flips to discharge the bottom test mass. So as I mentioned before, that TST gain has now gotten up to the 10% level. And this is not compensating for it at all. And then once you compensate for it, you see that this is now including that compensation as well as the compensation for the optical gain factor. You get your errors your systematic error comes down significantly, although your statistical uncertainty is still large, and that's because of the lack of just fewer measurements to pinpoint the actuation parameters. And then for the perfect calibration, you get rid of your systematic, but you've still got these uncertainties associated with just not enough measurements. Still, we're less than 10% in 10 degrees, which was the goal. All right, so finally, I just want to mention how we do this all in low latency. So we have an online calibration system, and in order to get our latency down as much as possible, we have put as much of that calibration process as we can directly in the front end. And by the front end, I mean the computers that actually directly control and impact the interferometer. So we do as much of the calibration process as we can in the front end, but we can't get everything perfect in the front end yet. So we then have to take that output and correct it a little bit. In addition, we can't compute any of the time-dependent gains in the front end yet, so we have to do that afterwards. And then the rest of it is done by the same GST-LAL pipeline that does the offline calibration. It just runs in a slightly different mode. It has different filters. Now it's got corrections to actuation and sensing instead of the full actuation and sensing, but it still does the computations of the time-dependent factors, and otherwise looks the same. The latency of this process is on the order of 10 seconds. Now there are larger latencies associated with getting that data all the way to the detection pipelines and getting the results populated in our gravitational wave candidate database. I don't know what that latency is at. Kip, do you happen to know?
40 seconds.
40 seconds.
Wait, what is the detector to over?
Okay, so we're at about 40 seconds overall. So 40 seconds after a gravitational wave hits LIGO, we should have an event uploaded. And then it might take weeks for us to send it to our partners. But that is human-related delay, not, not software. Okay, so this is what the online calibration system looks like. Here's what's in the front end. You've got your error and control signals right there in the front end, computed right there in the front end. You have your filters for the different stages of the actuation and the sensing right there in the front end. You do your filtering, whiten everything, because we've got to whiten things because we can't record anything in double precision. But anyway, that gives us what we call delta L residual and then our delta L control signals. So these are partially calibrated residual and control signals. Then we need to finish it off. So we need to multiply by correction filters, and we need to multiply by the appropriate gain factors for each of the stages. Now note that for the entirety of our first observing run, we computed these factors, but we never actually corrected H of t with them in our online calibration process, just because it took a long time to figure out the right time scale at which to average these, the right way to do it all, the right way to make sure we don't any glitches that cause these values for the gain numbers to jump significantly at some point in time. You don't want to then put that glitch back into H of t at some exaggerated value. So we had to think about all these things, and these were never turned on in 01 for the online process, but they will be in future runs, and they were computed throughout 01. Okay, and then finally you put it all together, you divide by L, and you get your H of t. The order of operations here was switched around a little bit. That's just to make things a little more computationally optimized. Okay, so just to summarize, our online calibration for advanced LIGO is running better than it ever has before, but it still does require improvement. We've still got work to do. We need to move more and more of the process into the front end to improve that latency even more, and we need to actually turn on those corrections for the time dependence online. Once we can turn on those time-dependent calibration factors, that does things like improve the sky maps we send to our electromagnetic partners. So that's an important one. Our offline calibration has reached an excellent level of calibration accuracy. Once we get everything added in there, including corrections for the coupled cavity pole, we can be within 5% errors in magnitude and 5 degrees in phase, which is beyond what was asked of us. There's more work to be done. We do need to finish putting all the time-dependent corrections in there, so like get that coupled cavity pole calculation and updating filter in there, figure out what's going on with the PUM and UIM stage gains, and then we also just need to optimize everything for efficiency. And finally, we need to improve the latency of the offline calibration process. So that order of weeks is too long for many people to be comfortable with. So more manpower and more automated systems will help with that. But calibration so far is better than it's ever been, and our detectors are better than it's ever been. So it's an exciting time to be in gravitational wave science. That's all I had. 401, not bad.
So maybe we have a couple of questions. So I do have a question. So how do you measure the statistical uncertainty in the calibration figures that you were showing? How will that go?
Well, they use, the statistical uncertainties use things like, gosh, I'd have to look back at the paper for that. It accounts for things like how many measurements we've taken. That helps reduce the uncertainty. And it also accounts for the calibration factors. No, those go into the systematic. But no, so the SNR we use to calculate the calibration factors is going to lead to, there are statistical fluctuations in the values we compute for kappa, each of the kappa values at each point in time. That has to do with the SNR of the injections that we use to compute them. So the level of accuracy to which we can compute the calibration factors, as well as, I believe it's the number of measurements that we can get, I forget exactly how that enters in, are going to be the things that determine the statistical uncertainty. I can show you, we've got a draft of a paper that I could show you, but we haven't put together the final thing yet that describes the full uncertainty budget and how we compute each of the statistical uncertainties and the systematics to better explain that. But yeah.
You have CO3 quality calibration online in O2?
That's the goal. Yeah, yeah. We just need to get the hurdle between O1 and O2 is to get the updating filters for the coupled cavity pole. Yeah.
What's the difference between C00 and C01?
Yeah. C00 is what we call our online frames. So those are the things that come right out of the online system. So those right now don't correct for any time-dependent gains, but on top of that, they may contain times of large error due to dropouts at the input of the calibration end. We actually haven't seen that since like October. I think we've taken care of those problems. And then the C01 frames also don't include any time dependence, but that was run offline. So all the data that we had available to us was used to compute the C01 frames. So they're the same calibration process, actually. Well, okay, there's another difference. The C00 frames, half of that process was done in the front end and half was done by the GST-LAL pipeline, whereas the C01 frames, it was all done by the GST-LAL pipeline. However, the differences between what the front end does, the differences between this process, what the front end does, plus the corrections done by GST-LAL is within, I think it's 1% in magnitude and less than a degree in phase of what this procedure produces. So this is what C01 did, and this plus that is what C00 did. And assuming there were no data dropouts, the two should be the same to within 1% and 1 degree, I think, between 10 hertz and 2 kilohertz. They'll do different things below 10 hertz, but we don't care about that. Yeah.
So since you said the time-dependent factors are not known for O1, I guess all the data you've been showing was from measurements on the engineering runs within LIGO, or when did you actually?
Which data are you referring to?
Well, you showed plots indicating what the errors would be if you had the time-dependent corrections turned on or off these plots, right? So
yeah.
So is this known through the engineering run? Measurements on the engineering run?
No, this is from our O1 models. This is from the O1 models, but in our uncertainty budget, we can factor in what it would be without the time-dependent gains and what it would be with the time-dependent gains. So it doesn't have to be based on, you don't need the actual H of T sitting there. But we are going to have, in O1, we are going to have calibrated data that has at least the TST and the sensing gains turned on. We're in the process of making that. So that data will eventually be available from O1.
Okay, so
yeah.
post-process.
Yeah, we'll post-process with that.
So you, at the outset, you showed this strain sensitivity curve.
Oh yeah.
So how much does that change with time? But you show us the error in calibration, which is like 5%. Does that mean the green line there will vary, say, 5%?
Oh, well,
The green line actually vary much more than that. It's just your ability to know where the green line is.
it's our ability to know where the green line is what's within 5% in magnitude.
So how much does the green line
Change over time? Well, it depends. So, for example, at Livingston, where we are no longer accurately modeling the actuation TST stage because that gain has gotten pretty far off and we haven't yet compensated for it, I think we've dropped something like 5 to 10 megaparsecs in our BNS horizon distance due to that. But that's just an error. That's not like our real horizon distance has dropped. It's just an artifact that the calibration has not correctly modeled something, so it appears that our horizon distance is lower. So things like at the 10% level in calibration, I haven't done the propagation to see if this is the only cause, but we've seen fluctuations of like 5-ish megaparsecs in this range.
So who declares when the thing is failing to work right, when he's falling out of block, or some local noise that he screws things up?
Well, people on the site do characterization, noise characterization work. I mean, there's an automated locking system that determines when that gets the interferometer into resonance and holds it there. And there's an automated system to bring us to that point, and then there's a human that sits in the control room at both sites and determines, okay, did we successfully achieve this low noise resonant state, A, and B, is no one doing commissioning work right now, which requires a human to understand. And then they push a button that actually says observation intent, which means that we intend to do observations right now. And then there's people who sit on site and flag things like a delivery truck just came in, which led to large noise. And I don't know if that was quite your...
You will also see that in the calibration, that you can check that they actually made the right decision.
Oh, you'll see when there are large noise sources on site, it certainly shows up in the data and people see it. There's a whole task of people called detector characterization that sit there and characterize the data and the detector over time and look at plots of frequency energy across the whole frequency band to see when there might be some excess noise source somewhere and try to characterize what it is.
So let's continue the discussion upstairs and please find us.